started. Okay, so this week we are learning a lot of different rules, and it is going to seem a bit overwhelming, but it's not so bad. And one that a lot of people struggle with is Descartes' rule of signs. So this is used specifically to analyze polynomials. So a polynomial is a function where you basically have a series of terms and you have exponents on those terms. And we usually write it from highest to lowest. We don't have any square roots, no absolute values, no fractions with variables in the denominator, none of that stuff. It's pretty straightforward. All the exponents are whole numbers. All of our coefficients are real numbers. So there's no complex numbers in your function. And some terminology, most important that we're going to be using today is degree, but the term with the highest exponent is called the leading term, with the number in front being the leading coefficient, and then that highest exponent is called the degree. So what we do with polynomials is find zeros. You're going to be asked quite a bit to find the zeros of a polynomial, and those are where your y value is equal to 0. So you set your function equal to 0 and you're solving for x. So basically, any x-intercept is considered a 0. We may also have zeros that are complex numbers. So you won't see them on a graph, that they're not x-intercepts, but they're still zeros. And y-intercepts are not zeros, because we're looking for specifically where y is equal to 0. So we don't care about where x is equal to 0, though that's potential x is equal to 0 when you solve, but we're looking specifically where is the function itself equal to 0. We're solving for x. So Descartes' rule of signs basically tells us how many positive zeros we should expect, how many negative zeros we should expect, and then how many are complex numbers. So instead of having like you know, trying to guess, well, I think I have like 5 positive zeros, we have an idea of how many there are. And this rule came about by Rene Descartes, which is why it's named after him. And it was discovered in 1637. And he basically just discovered that there was a relationship between the function and the number of positive zeros. And then other mathematicians expanded it out. And this rule is very helpful if you're trying to determine the zeros for a function and you don't have technology. So if you're wondering, well, why am I learning this? This is so you understand the concept and what's going on. You get some practice with logical thinking. Plus, when a computer or some sort of application is finding the zeros, it uses these rules to kind of make it go quicker. So this also gives you some understanding of what's going on in the background if you're using a calculator or something like that. So you have your polynomial, f of x, and it has to have a non-zero constant term. So you have to have a number at the very end. The number of positive zeros are either the same number as the number of sign changes. So you look at all your coefficients and you count how many times it changes sign as you go left to right. And that tells you how many possible positive zeros we have. And then they always come in pairs. So then you subtract that by 2, and that will give you another possible combination. So like if you found that there was 4 sign changes, you could have 4 positive zeros, you may have 2 positive zeros, you may have 0 positive zeros, but then you stop because we can't have negatives. Negative number of zeros, that doesn't make sense. So the number of negative real zeros, it's basically the same rule, but you look at f of negative x. So you plug in a negative for your negative x for your function, and then you simplify, count how many times your coefficients change sign, and then you subtract by 2. And then the number of complex zeros, you have the total degree. The degree tells you how many zeros you have, and so they have to add up to the degree. So the complex are just whatever is left over that makes it add up to the total degree. So You count how many sign changes there are, you subtract by 2. So I give the example of 4, 2, 0. If you have an odd number, like if you have 5, you have 5, 3, 1, and then you stop because your next number is going to be negative. So you can get multiple possibilities. This is not guaranteed, like for sure there's 4 zeros. It's just giving you the possible combinations so that you have an idea of, well, I think there's this many positive, this many negative, and so on. So I like to make a chart, and so I've got that here in the bottom left. And even if it doesn't ask for the complex ones, I just find it anyway because it just is completeness. So we want to determine the different possibilities for the number of positive, negative, and non-real complex zeros of f of x equals 2x to the fourth plus 3x cubed minus 5x squared plus 4x minus 1. So first, you want to start with the degree. So the degree of the polynomial is that highest exponent. So our degree is 4. And so these need to add up to 4. The total is going to be 4. I'm going to just put that right here, but I'm not going to put it into my box because I fill that out last. So to find the possible number of positive zeros, you look at the coefficients. So I'm just going to ignore the variables and write my coefficients. And then you count how many times is it changing sign. So we go from positive, we go left to right, positive, positive, it's not changing sign. But then we go from positive, negative. Then we go from negative to positive, and then positive, negative. So we have 3 sign changes. So what that means is that we have possible 3 possible positive zeros, or 1. Try to divide this into 1 possible positive 0, because they always subtract in pairs, and then your next number would be negative, so you just stop. So we could have 3, or we could have 1 possible positive zeros. So that's why I put that in my table, 3 and 1. Next, to find the possible number of negative zeros. So we got possible number negative zeros. So you have to actually first plug in negative x into the function. So 2 times negative x to the fourth plus 3 times negative x cubed minus 5 times negative x squared plus 4 times negative x minus 1. Numbers that, or exponents that are odd, are going to change signs, because a negative to an odd exponent comes out as negative. So this the term with the cubed is going to change signs, and that's going to become a negative 3 in that coefficient. And the one with just the x, the negative x, you can see that when you simplify that, that will become a negative 4x. The evens keep the sign because the negative will cancel out. So when we simplify this, we get 2x to the fourth. Then we're going to get a minus 3x cubed. Then we are going to get a minus 5x squared minus 4x minus 1. And so then again, you're looking at the coefficients to see where it changes signs. So we've got, I'm going to just put it to the right here, 2, negative 3, negative 5, negative 4, negative 1. And so if you're counting how many times it's changing sign, we go from positive, negative, but then we stay negative. So there is 1 sign change. So we could have one possible negative zeros, and we can't divide that by 2, so it's just going to be 1 in both columns. And since it's the same number, this tells us we have to have one negative real zero. So one of the zeros must be negative. As far as positive goes, we could have 3 or we could have 1. So once I fill this out, then I look at the total. The total that has to be 4. These have to add up to 4 because that's the degree. And so the number of non-real zeros, the complex zeros, are this whole column needs to add up to 4. So this is like a total right here. So I've got 3 plus 1, that's already 4. So they're going to be 0 complex zeros. Or in the next column, I have 1 plus 1, which is 2. So I need 2 more in order to add up to 4. So you can see the number of non-real zeros can also, in this case, goes up by 2. So we have 2 combinations here, basically. If you were to find the zeros, we would have 3 of them that are positive, 1 negative, or you would have 1 that's positive, 1 negative, and 2 that are complex. So if you were trying to figure out the zeros, knowing that one of them has to be negative can help you, because then you can use synthetic division and check negative numbers first, because you know one has to be negative. And then once you found your negative 0, you can stop looking because that's the only one that's negative. So it kind of narrows down your possibilities. I'm going to bring up Gizmos, and we're going to graph this function here. So we're going to graph it because zeros are related to x-intercepts. And so the positive and the negative zeros, those are x-intercepts, and then the complex won't show up. So I'm going to put in our function. F of x equals 2x to the 4th plus 3x to the 3rd minus 5x squared plus 4x minus 1. So I'm going to zoom out just to make sure we see the whole thing. And I'm going to adjust our x-axis. You see it a little better. Okay. So this is our 1 negative 0. We're guaranteed to have a negative 0, and we've got it right here. And then we either had 3 positive zeros or 1 positive 0. So if you look at your graph, there's only 1 positive 0 here. So out of our 2 possible combinations, our actual answer for the number of zeros is the second choice right here. That's our actual answer. So we have one positive 0, 1 negative 0, and then the other 2, if you were trying to solve this, would be complex numbers. So we knew it was going to be one of these 2 combinations, and the graph allows us to see which one it is. So let's look at this second example. Determine the number of possible positive and negative real zeros for g of x equals 3x squared plus 4x to the 4th minus 6x cubed plus 5x squared minus 6x plus 1. So it doesn't specify the number of complex or non-real zeros, but I do it anyway just for completeness. So our degree here is 7. So we're going to have a total of 7 zeros. So that's the highest exponent. Our degree is 7. So we have to make sure that all of our numbers add up to 7. So first we're going to find the possible number of positive zeros. And we look at the coefficients. So we've got 3, 4, negative 6, 5, negative 6, and 1. We don't need to add zeros in there because zeros are not positive or negative, so it doesn't really count. So we just look at the actual coefficients we have. So we have positive to positive, but then we go from positive to negative. Then we go from negative to positive, and positive, negative again. And then we go from negative to positive. So you count these, we have 4 sign changes. So these always go in pairs. So we have 4, 2, and 0 as our possible combinations. So we're going to have 3 possible combinations here, because we just keep subtracting 2 until you get to 0 or a negative. And these have to add up to 7, so I can put that in as my total. Next, we want to find the possible number of negative zeros. So g of, and we plug in negative x equals 3 times negative x to the 7th plus 4 times negative x to the 4th minus 6 negative x cubed plus 5 negative x squared minus 6 negative x plus 1. So everything with the odd exponent is going to switch signs. The things with the even exponent are going to stay the same. So this will give us negative 3x to the 7th, because that switches signs. Then we have an even exponent, so that's going to stay positive x to the 4th. Odd exponent, so our negative 6 is going to become a positive 6x cubed. Even exponent, so that 5 will stay positive. We've got an odd, that's going to switch the negative 6 to a positive 6, and then a plus 1. So now we want to look at our sign changes again. We go from a negative 3 to a positive 4. Then we stay positive, stay positive, stay positive, stay positive. And the rest of the numbers are all positive. So we have 1 sign change. So 1 sign change means, once again, there is only 1 negative 0. And so we just fill that in for every column there. So now we need to have these add up to 7. So our first column adds up to 5, so we need 2 more to get it to 7. And then we've got 3, so we need 4 more to get up to 7. And then 6 more to get it up to 7. You can see they always come in pairs. So we have 3 possible combinations here, and we don't know which one we have. We just know we're for sure having a negative 0. So I can go back to Desmos and graph this. We've got g of x plus 3x to the 7th plus 4x to the 4th minus 6x cubed plus 5x squared plus minus 6x plus 1. Okay, so you can see only 1 0 is in the negative side. And it looks like we've got 2 positive zeros right here. So out of these 3 choices, we are in the middle. We have 2 positive zeros, 1 negative 0, and that means there are 4 complex zeros if you were to try to factor this and solve. Same type of question, and here we've got decimals. And you may think, oh my gosh, with decimals this is more complicated, but it's the same rule that applies. You don't actually care what the numbers are, because all we care about is the sign. So first, we will look at the degree. And so the highest exponent here is 4, so this degree is 4. So we're going to have 4 zeros total, so it has to add up to 4. So we have possible positive zeros, possible number of positive zeros. So So just look at the coefficients. I've got a negative 0.6, 0.8, negative 0.6, 0.1, negative 0.4. So I go from negative to positive, positive to negative, negative to positive, positive to negative. So you count those again, we have 4 sign changes. So I'm going to have 4, 2, or 0. So I'm split this up. 4, 2, or 0 for our possible positive zeros. And our total needs to add up to 4. So the one that I have 4 possible zeros, I can automatically fill in a 0 there because, well, it has to add up to 4. So if 4 of them are positive, then I can't have any of the others. So those are for sure going to be 0. So now we're going to look at the possible number of negative zeros. So I have q, and I'm plugging in negative x, negative 0.6 to the negative x fourth plus 0.8 times negative x cubed plus 0.1 times negative x minus 0.4. So anything with an even exponent, the coefficient it stays the same, it doesn't change sign. Odd exponents, the coefficient changes. So this is going to be, we've got an even exponent, so this stays negative. Then we've got an odd exponent, so it becomes negative. Then we've got odd, this is going to become negative. And then we've got a negative. And we end up with all of our coefficients negative, so we have 0 sign changes. So we've just got to plug in 0 for all of the negative possible zeros. So now we just fill in the remainder. If we have to add up to 4, if there are 2 that are positive, then 2 must be complex. And if there are 0 positive, 0 negative, then they all must be complex numbers. So we can look at the graph to determine which one it is. So I've got q of x equals negative 0.6 x to the fourth plus 0.8 x cubed minus 0.6 x squared plus 0.1 x minus 0.4. Okay, so I'm going to zoom in so I can see this. Okay, so you can see it never actually touches the x-axis. It's below it. And then it just stays in the shape. What this means is that we're going to have 4 complex zeros because there are no x-intercepts at all. So out of these 3 choices, the actual combination is the last one here, where we have 0 positive, 0 negative, and there are 4 that are non-real. So this is my last example. Same thing, we've got 1 over 1,000 x to the 6th plus 1 over 100 x to the 4th plus 1 over 10 x squared plus 1. And again, even though it looks gross with the fractions, it doesn't matter. It's, it's not going to make a difference. So we have first degree. This is degree 6. So I'm going to start with the possible number of positive zeros. And I just look at the coefficients. 1 over 1,000, 1 over 100, 1 over 10, and 1. These are all positive, so there are 0 sign changes. So that tells us that there are 0 positive zeros. I don't have any other combinations, just 0. My total here has to add up to 6. So next, we want to find the possible number of negative. Possible number negative zeros. And so our function is called QT. That is allowed. You're allowed to have more than one letter there. And we're plugging in a negative x. So I have 1 over 1,000 negative x to the 6th plus 1 over 100 negative x to the 4th plus 1 over 10 negative x squared plus 1. All of these have even exponents, which means the negative is going to cancel out. So what we end up with is the same function we started with, because all of the negatives are canceling out. And this is actually an even function. This is something else that we talk about this week, is even and odd functions. This one's considered an even function, because if you plug in a negative, you get the same thing if you plugged in a positive. So we have 0 sign changes again. So I've got 0. And so I've only got one combination here. That means I have to have 6 that are complex numbers. If you were to try to factor this, it wouldn't factor. And if you tried to solve this, you'd only get complex numbers as your answer. And if we graph this over 1,000 x to the 6th, whoops. I don't think it likes me having more than one letter there. I'll just call this one T. 1 over 100 x to the 4th plus 1 over 10 x squared plus 1. This is another one where it never crosses the x-axis. We have 0 x-intercepts, but we still have 6 zeros. They're just all complex numbers. So they don't show up on the graph, but they still exist. So we've got only one possible combination, and you can see that the graph reinforces that. So that's Descartes' rule signs. And when you're entering this into ALEKS, what you would do is they'll give you like the table, and so you would fill in something like this table, and you wouldn't have the highlight part because all the problems only care about the possible. They don't care what is actual. So you just literally fill in a table just like this. Sometimes they may ask for just the number of positive, and you just separate your numbers by commas. So if we look at this problem, it said how many possible positive real zeros are there? You would say 4, 2, 0. So if there's not a table, you would enter each one with commas. Otherwise, if you have a table, you just literally fill it in like this. So that's all I've got for you guys. Thank you, and I hope this was helpful.